All right, we're going to close out our study of Chapter 10 by looking at heating and cooling curves for water and other substances, as well as phase diagrams. So let's jump into these heating and cooling curves. All right, and just for an example, we're going to use water for our curves, but any other substance could be used here. So a heating curve for water is constructed by using a two-dimensional plot of temperature on the y-axis and heat energy on the x-axis, all right, given by the symbol Q. So we know there's a couple interesting points along this heating curve that we're going to talk about for water, and that's that we know at 0 degrees C, that we'll put down here, water is going to be in its ice form, and then up here at 100 degrees C, water will boil and then go from its liquid to gas form. All right, so we'll go ahead and put in a point down here, and let's just call this minus 20 degrees C. And that's where we're going to begin our little journey here. And notice that we're doing temperature versus heat. All right, these two properties or terms can get confused quite often. Temperature is the measurement of the thermal energy, and Q is actually the amount of heat being applied. All right, so what we're going to be looking at here is if we start at minus 20 degrees C, and we're talking about water, we're certainly going to be in the ice form. All right, and what we can start to do with ice, and let's say we have ice at negative 20, all right, we put it in a freezer, set it at minus 20, that ice can actually be minus 20 degrees. We can actually put ice into liquid nitrogen, and that ice would be at, if you put it in there long enough, and it was possible, you could get down to, let's say, like, negative 200 something degrees. All right, so you can cool ice below 0 degrees. That's not a problem at all. All right, but as we heat the ice up, by that I mean we're going to increase our value of the x-axis. The temperature of the ice is also going to go up. So we'd imagine to start to see a curve exist like this. All right, and we're not talking about vapor, pressure, or anything like that. This is just going to be a linear increase in heat and temperature. All right, and then we hit kind of a very special point, and that's going to be the melting point of water, or ice, if you will, as it transitions into liquid water. So what's going to happen is it's going to actually stall at 0 degrees, all right, as we add more and more heat. All right, this is called the latent heat of fusion. All right, and we're going to define all these terms shortly and mathematically as well. But what ends up happening here is once we hit 0 degrees, we begin to transition from the solid to the liquid. And what's going to happen is we're going to start transitioning, and that requires heat. All right, that's why the value of the X or Q is increasing, but we don't see any temperature change. All right, not until we're completely changed into the liquid form. All right, so once we change into the liquid form, we begin increasing our temperature. So our liquid water is now going from 0 degrees, and it's going to go up until it hits a magic point. And that magic point, of course, is 100 degrees C, where we're also going to have another stall, or what we call the latent heat of vaporization. All right, so what's going to happen now is we're going to start transitioning from liquid to gas without an increase in temperature, but this requires an increase in the amount of heat added. Then once all the liquid is transitioned into the vapor phase, we can heat our now vapor or steam above 100 degrees C. All right, so what you see here is something we talked about earlier, that liquid water can never be heated above 100 degrees C. All right, without doing some neat little tricks that we'll talk about here in a minute. Okay, however, we can heat water above 100 degrees C if it's in its vapor phase, all right? So vapor phase, we can heat water above 100 degrees, just as we can cool water below 0 degrees C if we're in the solid phase, all right? So liquid water is restricted to exist only between the temperatures of 0 and 100. Water vapor is restricted from 100 up until, you know, how high you can heat the steam in a container. Same with the solid. You can go below 0 degrees C with that, all right? So there's a few points along this curve that I'd like to investigate. So there's this here, then this flat point here, this here, 4, and 5. All right, so there's 5 points along this curve that we're going to be looking at here. All right, so let's go ahead and look at number 1. What are we doing on the curve at 1? All right, so at 1, we are what we call warming ice, okay? So we are ice warming. And this can be defined by the following equation. The amount of heat added is equal to the mass of the ice times the specific heat of the ice and the change in temperature, all right? So that is the equation that will tell us how much heat is required, Q, to change a specific mass of ice with a specific heat a certain amount of degrees, all right? So let's talk about these properties. Q, of course, is the heat added. M is going to be equal to the mass of the material. Of course, the more material you have, the more heat that's going to be required. So you can see they're directly proportional there. CS, this is called specific heat, and it's intrinsic to the material, all right, and the phase. Solid water has a different specific heat than liquid water will, all right, so we have to be very careful where we're looking at, okay? There's also another one that's not being used in this equation, okay, and it's called the molar heat capacity. All right, and when the molar heat capacity is used, we're going to be dealing with moles of the substance rather than the mass of the substance. So do you see the difference in the two equations? When you have specific heat, that's related to the mass, all right? When you're dealing with the molar heat capacity, that's the moles that we're dealing with, all right? So depending on if you're given the specific heat or the molar heat capacity, you'll use these two equations. Delta T, of course, is going to be the change in temperature. All right, so that's how much we're changing the temperature, okay? So that's how we're going to mathematically figure out how much heat is required to move on the curve at point 1, all right? To move on the curve at point 2, now we're dealing with something called ice is melting, all right? It's not warming, it's now melting because we've now hit the melting point of ice and we're transitioning to water, all right? So if we look at the curve there, it's flat. There is no delta T, all right? So our equation is going to look a little bit different where Q is going to equal N, so this is the moles of water, times the delta H of fusion, all right? So back in the Clausius-Clapeyron equation, we were dealing with the delta H of vaporization. That's because we were dealing with liquid to vapor. Now we're talking about ice melting. So we're going from solid to liquid. We're not using delta H of vaporization now, we're using the delta H of fusion, all right? So it's a much simpler equation, all right? Notice we don't have any delta T here, all right? The third point is going to be water warming. So kind of see the pattern here. 1, ice was warming, okay? We had a change in temperature. 2 is melting without any change in temperature. 3, we're having a change in temperature, but now what we're doing is we're warming the water, the liquid. All right, so the formula is going to be identical to the one we saw in segment 1, where we have Q is equal to the moles times the molar heat capacity, delta T. Now, we have to be careful. The moles, yeah, we're using the same amount of material. However, we have to be careful here with the molar heat capacity. We're talking about the molar heat capacity of liquid water, not solid water this time. All right, 4. Okay, this is going to be another transition without without temperature change. So what we're doing here is we're taking liquid and we're converting it to vapor without any change in temperature. So at this point, this is going to be water is vaporizing. So now we're going to need this equation. Q equals N delta H of vaporization of water. All right. So our water is going to vaporize here, not melt. So we need delta H of vaporization, not delta H of fusion. And the final leg is going to be steam warming. We're actually just heating the steam. If we look, we're going to have an increase in temperature at the 5th leg here. So our equation for the temperature increase is going to be Q equals N for the moles of steam that we'll be warming, the molar heat capacity of steam times the change in temperature for that steam. All right, so those are our 5 equations, and they repeat. All right, there's a pattern to them. However, the one thing that's going to change is what molar heat capacity for what substance you need and what delta H for which transition you need. All right, so we can do an example. All right, I'll admit this is much more straightforward and less cumbersome than going through the Clausius-Clapeyron equation. But let's go ahead and look at how much heat is required to convert 50 grams of liquid water at 25 degrees C to steam at 150 degrees C. All right. So it's tempting just to say, oh, my delta T, I see that. That's going from 25 to 150 degrees. I've got this amount. Boom, I'm just going to pick one of those equations and run with it. I'll caution you that you need to draw the map first, all right? So that map, this is the heating curve. We're going through 2 different phases. We're going from liquid to steam, all right? So we need to be careful and figure out what that curve looks like when we do that. All right, so over here I'm going to put T on my y-axis and Q on my x, and I'm not dealing with ice or fusion here, so I'm going to start straight out at 25 degrees C here. All right, and at 25 degrees C, I'm at liquid, and it looks like I'm heating it, right? So I'm going to heat it. So this is water warming, and then I hit 100 degrees, right? And once I hit 100 degrees, then I'm going to do this latent heat of vaporization, and then it's going to transition, it's going to transition to that heat of latent heat of vaporization, and then I'm going to start warming the vapor up to 150 degrees here. All right, so I have 1, 2, 3 equations I need to deal with. All right, and it's convenient to call them Q1 plus Q2 plus Q3 is going to give me the total amount of heat that I need. All right, so this how much heat at the beginning of the question, that's Q total. All right, and what I have to do is figure out what amount of heat do I need to get through 1, what amount of heat do I need to get through 2, and what amount of heat do I need to get through to 3. All right. so let's get started, and let's look at Q1. All right, Q1 is going to be N times Cm delta T. All right, so how many moles of water do we have? What is the molar heat capacity of water, and what is my change in temperature? All right, so the constant for water, the molar heat capacity of water, is a constant. And let me say this is for H2O liquid, is equal to 75.4 joule per mole degree C. Right? That's not a number you necessarily need to memorize. That would be provided to you if I were ever to give you this to you on a quiz or an exam situation. All right. Okay, so we've got that. That's a constant. Now N, what's that? That's the moles of water, right? Well, how many moles of water do I have? They tell me 50 grams. All right, so I got to do a conversion here. So the moles of H2O is equal to 50.0 gram. All right, so I got to convert grams to moles. So I do that with the formula weight of water, which the formula weight of water is 18.0 gram per 1 mole. And I get that by going to the periodic table and looking up the molar mass of 2 hydrogens and 1 oxygen. Of course, that'll give me the 18 grams. So my grams cancel, and now I just take 50 divided by 18, and I get 2.78 mole. So got that. So the last thing I need is delta T. All right? And that's going to be final minus initial. That's what a delta always is. So it's T final minus initial. So it's tempting to say, oh, my final temperature is 150 degrees. No, you're looking at this one section, just the Q from on leg 1. And that runs from 25 to 100. So your final temperature on leg 1 is actually 100 degrees. All right? So it's 100 degrees C minus 25 degrees C. And that is going to give me 75 degrees C. All right? Now, is degrees C cool? Yeah, because in my constant, molar heat capacity is a constant that has a degree C in it. So that's totally fine. So now I'm going to put it all together. Q1 is equal to 2.78 mole times my molar heat capacity is 75.4 joule per mole degree C times my delta T is 75 degrees C, and I get 15,721 joule. All right, so that is my first Q1. All right, so I'm going to do the same thing for Q2 now. Well, not the same thing, but I'm going to calculate Q2. So Q2 on the curve is a transition that happens without a change in temperature. So this is that latent heat of vaporization. All right. So that is going to be equal to N delta H, and the process that we're going through is vaporization. All right. So what's nice about this is we already know the moles, all right, because we're not losing any of the material. All right. So it's 2.78 mole is my N. Now my delta H of vaporization. So that's a constant that would be provided to you. It's also in the appendices of your textbook. And it is given as 40.67 kilojoule per mole. Oh, goodness. Right, so this is going to be a little bit of a tiny pain, right? Because if we look back to what we did before, our constant, the molar heat capacity, was given in joules. All right, so when we calculate our heat value, that came in at joules. All right, there's a few ways you can handle this. You can go ahead and convert the delta H of vaporization now, or you can just simply convert your heat value to joules when you're finished. All right, so it's either way. I honestly am just going to go ahead and just convert my Q to joules when I'm finished. All right, so Q2 is equal to 2.78 times 40.67. All right, my moles will cancel, and that's going to give me kilojoules. So when I do that, I wind up with 113.063 kilojoule. All right, and what I'm going to do now is convert that to joules. So Q2 is equal to 113.063 times 10 to the third joule. All right, so I just multiply that number by 1,000 to get to joules. All right. Finally, I need Q3. So Q3 is going to be where we are warming the steam. So this is going to require a change in temperature. So it's NCM delta T. All right. And my moles stay constant, so that's very nice. All right, so it's 2.78 mole. My CM, so this is the molar heat capacity for steam. All right, steam is different than liquid, so they're going to have different heat capacities. So this guy comes in at 33.6 mole degrees per degree, joule per mole degree C. Now, let's just consider the two numbers for a moment. So it's 33.6 for steam, and it's 75.4 for liquid. So what does that tell you? Well, it tells you that liquid water can absorb a lot more heat per mole than steam can. Any reason why you think that would be the case? Why can liquid water absorb more heat than water vapor? Well, I think it has to do with intermolecular forces, right? So the liquid water is much more tightly bound together, all right? So when it's more tightly bound together, there's more of it to absorb the heat, all right? So that's my reasoning there, all right? And delta T, we're going from 150 degrees C, that's our final temperature, and our initial temperature is 100 degrees C, not 50, all right? Because we started the leg 3 at 100 degrees C. So my delta T is 50 degrees C, all right? So Q3 is going to be 2.78 mole times 33.6 joule per mole degree C times 50 degrees C. And when I multiply those three together, I get 4,670 joule. All right. So now to do the end calculation is Q total is going to be equal to Q1 plus Q2 plus Q3. And I'll go collect my numbers. I've got the 15,721 joule. Make sure that's right here. Yep. And then I've got my 113,063 joule from Q2. And then finally my 46,070.4 joule for Q3. So just looking at these three, it's the same mass in each case, or same amount of moles. Which one took the most amount of energy? The Q1, the Q2, or the Q3 leg, right? And it turns out that it should be obvious that it's the Q2 leg that took the most. The transitioning from liquid water to steam water without increasing the temperature took almost 10 times as much as the next highest step, right? So there's a lot of energy required to go from liquid to steam. So adding these three numbers up, I get 133,4 454 joule, or if you went the kilojoule route, you get 133.454 kilojoule. All right, required to do that. Okay, so that's looking at what we call the heating and cooling curves. So we presented this in terms of the heating curve. All right, what's a cooling curve? Well, a cooling curve is just going in reverse. All right, so the heating curve, we went this way. All right, we went 1, 2, 3, 4, 5. A cooling curve, you're going to go 5, 4, 3, 2, 1. All right, but how is that going to affect your calculations? Only one thing's going to change. All right, it's going to be your delta T. So let's say you're doing a cooling from 5, 4 down to 3. All right, all the numbers are going to be identical. You're going to have the same moles. You're going to have the same delta H's. All right, you're going to have the same molar heat capacities. The only thing that's going to change is your direction of your temperature, your final minus initial. So honestly, the only thing that's going to change is going to be your value of Q. All right, Q, when it's positive, means you're adding heat. All right, so in a heating curve, you're adding heat. In a cooling curve, you're cooling things down, so you're releasing heat. So your Q is going to be negative. All right, so it's much like delta H, right? So all that's going to happen in a cooling curve is your Q's will be negative, all right, rather than positive. Okay, the last thing in chapter 10 that we're going to discuss are going to be something called a phase diagram, all right? And it's kind of a culmination of everything we've seen together, but let's go ahead and look at a phase diagram for water. All right, so a phase diagram, let me draw it quite large, is again another two-dimensional plot where we have pressure, all right, no, in units of atmosphere, not atmospheric pressure, but this is the pressure of the vessel, if you will, in atmospheric pressure, and then we have temperature here, okay? So, and we're going to put this in degrees C. All right, so we have a few things that we need to discuss on this curve. We're going to go up to 220 atmospheres. All right, now, atmospheric pressure is 1 atmosphere. All right, so this is 220 times higher pressure than atmospheric pressure. So you're talking about a vessel that is, highly pressurized. So this isn't something that you normally ever see or experience. So you would have to, be in very special types of vessels here. And we can go down to a pressure of 0.006, all right, atmospheres. So that's near, you need a pretty darn good vacuum to get down there, all right? So just bear with me while I draw these curves for a second. And this is not going to be to scale, by the way. So at 1 atmosphere here, 1 atmosphere is a special one because that is atmospheric pressure. So I'm going to extrapolate it across, all right? So what these curves are showing are different regions, all right? So over here in this kind of yellow shaded region is going to be the solid phase for water. In this green region, we're going to be in the liquid phase for water. And in this red region, this is the vapor phase or the gas phase for water. All right? So what does this mean? All right, so if we start to look around on this curve, at 1 atmosphere, let's look at this point right here. All right? 1 atmosphere where we touch this curve, if we're just to the left, over here, for example, that tells us we're in the liquid phase. If we're over here just to the right, that means we're in the gas phase. So at 1 atmosphere, where we transition from liquid to gas phase, this is atmospheric pressure of 1, that's defined as the boiling point, in this case, of water. All right? So remember, where vapor phase equals vapor pressure equals atmospheric pressure, that's where we're boiling. And we know that temperature to be 100 degrees C. All right? Okay, what about this intersection here? All right, where we transition from solid, if we're just to the left, to liquid, if we're just to the right. Well, at 1 atmosphere, that's known as the freezing point. And we know the freezing point of water to be 0 degrees C. All right? Okay, so pretty wild thing, I guess you could say, right? Because if you look at, let's say, 50 degrees C, and you went up to 1 atmosphere, where are we? Liquid water. No surprise. 50 degrees C, we're not boiling and we're not freezing. Okay, liquid water. No surprise there. All right? But we can do some fun things here with pressure. What happens at very low pressures? All right? So at very low pressures, look at some of this stuff. At very low temperatures, very low pressures, let's see where we could be a gas, for example. I'm going to put a red X here, or big red blob. All right, 50 degrees, I'm just saying plop it right down there. What phase are we in? Gas phase. At 50 degrees C, so you're telling me I can have steam at 50 degrees C. Yeah, you sure can, long as you have what? If we extrapolate over here, long as you're at what kind of pressure? Low pressure, so like this 0.006 vacuum, right? So under vacuum, low pressure, you could boil water, right? And we talked about that earlier, all right? So this is totally cool, or should make sense, right? Now, what about if we go to very, very high pressures and high temperature, all right? So let me put a green blob up here. Okay, 100 degrees C, my water should be steam, but I'm way up here at a pressure of 220 atmospheres, all right? That's telling me I'm at the what? Liquid? All right, so you're telling me at 100 degrees I can have liquid, or over here, 125 degrees, I could have liquid. Over here, 115 degrees, I could have liquid. So how's that possible? Well, we have to have very high pressures, all right? And that's how pressure cookers work. So like all the rage right now, and I have one of these at home, they're fun, are these Instapots, all right? They can cook things like hard-boiled eggs in a matter of minutes, or potatoes even in a matter of minutes. So how do they work? Well, they allow you to have water that can get up to a very high temperature. Because remember, at 1 atmosphere, what's the maximum temperature you can get liquid water? Right there, 100 degrees, okay? But if you increase the pressure of the vessel, all of a sudden, 100 degrees is easy to hit. You can be out here, all right, at 100 and let's say 50 degrees, as long as you have a high enough pressure. So that's some pretty neat stuff. That's how pressure cookers work. So think about pressure cookers allow us to have liquid water at higher temperatures than 100, and vacuums allow us to have vapor, water vapor, at much lower temperatures than 100 degrees C. All right, so pretty neat stuff. Now, there's one little oddity on this curve here. It's where it ends, all right? Well, there's two oddities. We're going to talk about this one first. This is called the critical point. And this is where things get weird, all right? This is the end of the curve, the end of the road, all right? And what this essentially tells us is this is where you've now hit the point where you are existing in something called a supercritical fluid. All right, it's not a new phase of matter. It's not like plasma is something totally different. We're not even talking about that. All right, this is called a supercritical fluid. All right, and when you're supercritical, what this essentially says is that water vapor cannot be liquefied no matter how high you jack up the pressure. All right, so let's say you are steam. All right, and you keep jacking up the pressure, jacking up the pressure, jacking up the pressure, and you're at the critical point, you can never get it into the liquid phase, all right? Because you hit the critical point and that's the end of the curve, all right? You just go supercritical at that point, all right? But if you're over here and you're a gas and you crank up the pressure, boom, you can cross into a liquid. You get enough pressure to do it, all right? So at the critical point, you hit something called the critical temperature, which essentially means water vapor cannot be liquefied no matter how high the pressure, all right? Conversely, at the critical point, liquid water cannot be vaporized no matter how high the temperature. So let's say you're over here, you're a liquid, you keep jacking up the temperature, jack it up, jack it up, jack it up, ding, ding, you hit the critical point. You can't go any further, all right? You cannot. So what does that mean? Well, you can't vaporize this liquid no matter how high the temperature. So what the heck is going on at the critical point? Well, at the critical point, you have something called a supercritical fluid that kind of exists as both a gas and a liquid at the same time. And you can look these videos up on YouTube. It's pretty wild. Carbon dioxide is something that they can get supercritical pretty commonly, all right? And it's actually used as a solvent in chromatography and, getting rid of caffeine from coffee beans and stuff like that. But yeah, just look up supercritical CO2 and you'll actually see the video of what it looks like. And you actually can't see it. It just kind of transitions into it and it just literally disappears, and you can't see it anymore. So it's a supercritical fluid, kind of an odd thing in nature. All right. Another oddity on this curve is something called the triple point. And what color haven't I used yet? Let's use gray. How does that look? Okay, right there. That guy's called the triple point. All right. And one way I've heard this kind of neatly put is that the solid exists in its boiling liquid or a boiling liquid. So think about that for a second. It would be like ice sitting in boiling water and water vapor coming out above the boiling water. All right, that's called the triple point. And the triple point is where it's a magic number between pressure and temperature where you're going to see all three phases existing together in an equilibrium. So pretty neat. And it only happens at one point. All right, so it's called the triple point. All right, so let's review. We've got the triple point there, all right, where all three curves intersect, if you will. And we have the critical point, right? That's where the curve ends between the gas and liquid phases. And then we have the normal melting point, right? The normal melting point is where you're what? You melt at 1 atmosphere. Over here we have the normal boiling point. That's where you vaporize at 1 atmosphere. Okay, so what the heck's this point? Well, that just happens to be a boiling point at some crazy pressure, all right? What is it exactly? Well, I don't know. You go over here and extrapolate and you say it's that pressure. And let's just for funsies say that's 100 atmospheres. All right. And then down here, it's that temperature, 150 degrees. All right. So that is a non-normal boiling point. All right. What's this over here? Well, that's a non-normal melting point or freezing point, depending on which way you go. All right. So that just happens to be away from the 1 atmosphere, and that's just where you're transitioning between the solid and liquid phase. All right. Something else that's worth noting here, and this only occurs in water. Look at this slope of this line here. All right, that the solid and liquid interface is. All right, that slope is going kind in what we'd say towards quadrant 2 or negative. All right, so it has a negative slope. And why is that? All right, so let's explain what that means. It means as you increase the pressure, okay, pressure is increasing. What are you favoring? Are you favoring liquid formation or are you favoring solid formation? All right, let's just take T equals 0 here, or temperature of equal to 0, and we're going to increase pressure. As pressure is increasing, we actually hang out in which phase? Liquid. All right, let's think about that. So as we increase pressure, we prefer the liquid phase? All right, why is that weird to me? All right, think about what a solid looks like, right? It's particles that are very closely packed together. Then a liquid, they're a little further apart. And then in a gas, they're very far apart, all right? So you would think as you compress or increase the pressure, you would slide towards the solid. Well, that doesn't happen to be the case here, all right, in water at least, all right? We just said as you increase the pressure, we favor the liquid phase. Well, this is one of those oddities in water, all right? Water, when it's a solid, is less dense than it is when it's a liquid. And you can easily prove this at home right now by just dropping a piece of ice in a glass of water. The ice will float, all right? That indicates that the solid water, or the ice, is less dense than water, all right? So why is that? Well, it comes down to this thing that I was raving about yesterday called hydrogen bonding. All right? Water makes this beautiful crystalline solid when it freezes, all right? And what ends up happening is you get this network of hydrogen bonding that is just right, all right? So that intramolecular distance has to be just right, and it's so beautifully ordered that it crystallizes into the ice there, all right? So compressing it actually causes it to move towards the liquid phase, all right? Because what you're going to start doing is disfavoring that hydrogen bond distance, and then the compound will actually start sliding past itself, all right? So compression of water disrupts that hydrogen bonding lattice, all right? So that's only exhibited in water. Other liquids don't have this hydrogen bonding lattice that water can get into. So other solids are more dense than their liquid. So if we were to draw the same curve for, let's do CO2, carbon dioxide, all right, its curve coming out of the triple point is going to look more like this. All right, and I'm not going to label the points because honestly I don't know them off the top of my head, but the important part is this solid liquid interface is a positive pointing towards quadrant 1, if you will, because as you increase the pressure, you favor what phase? Solid. All right, so that kind of is just pointing out that oddity in water. So the phase diagram for water has that solid liquid interface is pointing towards quadrant 2 or negative, and that has to do with that water's density decreases, all right, as you freeze it, all right. So solid water is less dense than liquid water. Into the story there, all right. Okay, that does it for chapter 10. All right, I will be posting some homework problems and be practicing those. All right, thank you very much.